So this work details our experience trying to automate the diagnosis of RAN performance problems. This is a joint work with Lee and Lee from Uber, who was previously with Alcatel-Lucent, and my advisor, Professor Jan Stoica. My talk today is about cellular radio access networks, or RANs. RANs consists of thousands of geographically distributed base stations that connects billions of us users to the internet every day. RANs are critical for both us users and also network operators. For users, they are important because they are our interface to the network, and hence all of our user experience is tied to the interaction with them. Naturally, we expect high quality of experience from all these networks. They are important to the operator because they form a crucial, if not the most crucial part of their network architecture, and so it's critical for them. Because of these, operators strive to ensure optimal performance of RAN 24 hours a day, 7 days a week, and 365 days a year. While RANs already have tremendous pressure to perform optimally at all times, emerging applications demand even stricter performance requirements. Applications such as driverless vehicles, home automation systems, connected transportation, all of these are becoming more mainstream. Many of these applications depend on cellular networks to provide always-on connectivity and require uninterrupted network access to perform critical tasks. This means that the performance of RANs are more critical than ever. Unfortunately, ensuring optimal performance of RAN at all times is hard. This is because RAN performance problems are still prevalent today. I'm pretty sure that all of us who have used cellular networks have experienced some problems with the network at some point in time, such as poor connectivity, connection drops, difficulty accessing the internet, and many other, to name a few. When problems happen in the network, we as users become frustrated. When we are frustrated, we tend to seek new network operators. We move from one operator to another, and operators lose money. Due to this reason, operators need to make sure that user frustration is minimal. Towards this, they must detect, diagnose, and resolve RAN performance problems as quickly as possible. Now, resolving a problem begins with detecting that a problem exists. Most of network operators today continuously monitor the network to find problems. To do so, they define certain performance metrics in their network. For example, an operator might say that I am going to monitor drops in my network. So they are going to monitor the drops in each of their base station. And when the drops go over a certain threshold, they decide to investigate why these drops happen. These investigations are not cheap. They take hours or even days for experts to resolve why things happened. And many times, it even requires field trips in these trucks with special equipments. This adds up to billions of dollars every year. Just to give you an example, one of the largest telecom operator in the US spends $22 billion every year for network troubleshooting and management. In this work, we seek to understand if operators can cut down this cost and time effort. That is, can they automate the diagnosis of RAN performance issues? Doing so would significantly reduce user frustrations and save time and money for the operator. In the rest of the talk, I will detail our experience working with a top-tier cellular network operator in the US in answering this question. Specifically, we have looked at a small portion of the RAN from this operator consisting of 13,000 plus base stations serving live customers over a period of a year. I'm not at a liberty to reveal much details about this network because of confidentiality reasons, but here is how a typical week looks like. The x-axis here is the day of the week, and the y-axis to the left shows the active users, or users who logged in at least once a day to this network. And the y-axis to the right shows the data volume that is carried by this network for every peak hour for 4 peak hours. There are around 2 million users every single day who use the network, and the network carries around 7 terabytes of traffic every peak hour. During the time that we spent studying this RAN, the network experienced thousands of problems. So thousands of tickets were created, and the operator spent a significant effort of time trying to figure out why things happen on the network. So one of the key things that we learned early on while doing this experience study was that existing RAN troubleshooting tools are fundamentally limited if you want to do automated diagnosis, mainly because they either lack or fail to exploit rich contextual information. Due to this, they are often slow and they are often ineffective. They could also arrive at incorrect diagnosis. Further, it leads to disagreements. Because we don't have contextual information, teams argue among themselves who should be solving this problem. Finally, in this operator's network, much of the effort is wasted because they keep solving the same problem again and again. And the problem recurs more than a bunch of times. So for accurate diagnosis, what we need is more fine-grained contextual information. What could this be? So the ideal approach to this problem is to log everything happening in the network. So you log every transmission in the physical layer, you log all the MAC layer frames and every IP packet, and later you can use them to figure out why things happened. However, this is not possible because of the sheer volume of data produced in these networks. In this work, we use a different form of fine-grained data. Connection level traces are commonly known as bearer traces that can be feasibly collected in today's operational network. A quick background on bearer level traces. This is the LTE architecture that most of us are familiar with. To communicate with the network, the user needs to establish a connection to the packet gateway. The UE does this by contacting the MME, who creates a tunnel between the user and the base station, which is known as the radio bearer. Once this bearer is set up, the UE requests the MME for setting up a connection, which then sets up a GTP tunnel between the base station and the serving gateway, and the serving gateway and the P gateway. These three tunnels form the EPS bearer. So in today's cellular networks, extensive statistics about these bearers can be collected. Some of the metadata that can be logged about the bearer could be statistics such as how many bytes of data were transferred, transmission time, allocation of resources, and so on. The setup, teardown, and modification of these bearers are done in the network using control plane messaging. So LTE networks can also log information about control plane procedures, which are a bunch of control plane messages happening in sequence. The bearer level traces, along with this control plane information, provide us rich information enough for doing automated diagnosis. To leverage these logs, we propose a three-step methodology for RAN performance diagnosis. In the next few slides, I'm going to explain our methodology and our findings and the insights that we obtain by applying our methodology on this operator's RAN. The first step in our methodology is to analyze performance issues by isolating the problem to RAN. The user experience for us could be affected by many things. For instance, it could be affected by the client. In this operator's network, we found that one particular device model caused problems for other people in the cell. Similarly, it could be problems with the internet. The internet could be unreachable, or there could be DNS issues and so on. Finally, there could be cellular network problems, which could be either RAN problems or core network problems. For this work, we filter out every problem other than RAN problems. How do we do this? There are two ways for doing this. We could either manually do this using an expert, but that is cumbersome and not scalable. But instead, what we do is we leverage the existing troubleshooting ticket system at the operator. They have rich history of solving many problems, and we can form filters and rules based on these trouble tickets to figure out if the problem is potentially a RAN problem or not. In the second step, we place these problems that we found in the last step into the following categories based on the broad underlying root causes. Coverage problems are among the worst for the users and also the worst for operators to resolve. Interference from nearby cells and users affect network KPIs. Base stations and MMEs could get overloaded and result in congestion, which could be problems happening in the RAN. In addition to these problems, there could be more subtle problems. For example, there could be hundreds of parameters that are tweakable in base stations and other network components, which could cause issues. Operators upgrade their network all the time. The upgrades could cause problems. And finally, there could be other reasons such as software bugs or protocol implementation problems. One thing to note is that the problems in the below category, the bottom categories are easier to solve, while the top category is harder. So each of these categories affect different network performance metrics. And we can use those metrics to put these problems into each of these bins. Further, for each of these categories, we associate potential underlying MAC or physical layer parameters that could be potentially influencing these problems. For example, coverage is mostly affected by the reference signal power, and drops could be affected by interference and so on. In the third and final step, we diagnose the root cause by modeling the KPIs associated with the problem. Operators monitor hundreds or thousands of performance metrics classified into several categories, such as accessibility KPIs that include connection drops, failure rates, retainability KPIs such as drop rates, uplink and downlink throughput, quality KPIs like block error rates, and so on. To diagnose a problem, we derive machine learning models for each of these KPIs at the bearer level using the parameters in our classification. So we talked about using physical and MAC layer parameters in each of those bins. We use them as features and come up with machine learning models to explain why things are happening in the network. The model explains the reasons for why the KPI is poor in terms of those features, thus diagnosing the problem. The performance metrics, although they are hundreds, could be categorized into two. They could either be event metrics, which are discrete values, or they could be non-event or volume metrics, such as uplink and downlink throughput, which are continuous values. For event metrics, we use classification techniques in machine learning, and for volume metrics, we use regression models. Let me take an example and show you how we model a key event metric, connection drops. In this operator's network, they monitor this KPI continuously and define an SLA. In the x-axis in this plot, we show the day of the week, and the y-axis shows the drop rate on that particular day. The operator says that once the drop rate goes above 0.5%, I am going to investigate because I am not within my SLA. Here we see that drops go over 0.5 all the time, so this is significant effort for the operator to investigate all these problems. Using our methodology, since connection drop is an event metric and KPIs can be classified into coverage and interference, we could build decision trees to explain these drops based from the bearer logs based on the physical layer parameters. Here is an example decision tree that we built for many of the cells in this network. We were able to achieve an accuracy of over 90% on average. Using this model, the operator knows exactly why drops happened. For example, here drops are mainly due to interference. This is quite surprising because intuitively we would think that drops happen because of coverage issues. Even more surprising is that this particular model in many of these cells distinguishes between two metrics that are theoretically identical, which are RSRQ and CQI. To investigate why this happened, we studied the impact of these two metrics independently. Here is the drop probability due to RSRQ, which is the reference signal quality at the UE, which tells you how much interference the UE is experiencing. And here is the same due to channel quality. Ideally, these two should have similar shapes, but they are not. If we plot the difference between these two metrics by converting them to a common base, say SINR, we see that the difference is huge, around 10 dB for most of the bearers. Though hardware variations and channel variation can result in some of these differences, 10 dB is quite a lot. The operator investigated this problem further, and what they arrived at is that the physical layer CQI does not have a CRC. What this means is that when the device sends a CQI, it could be bogus values. So what was happening was in many of these cells, the device was sending bogus values, which the base station thought that it was actual and converted to a valid value and resulted in drops. An example of volume metric is throughput, which is of great importance to users. We all have, at least in some point in our interaction with the network, downloaded some speed app. For diagnosing throughput issues, we use an information theoretical regression model, such as this one. It depends on several parameters. There is a MAC efficiency parameter here. There's a number of physical resource blocks allocated to the user, the transmission time, and it also includes a physical layer parameter, which is SINR, that is adjusted to achieve a certain desired error rate, which is agreed upon by the operator. Similar to the event metrics, what we can do is we can take the same bearer level traces and come up with the regression variables in this equation and predict the throughput using these parameters. Since we know the actual throughput that the UE obtained at any point in time, we can compare the predicted and actual values, and when they match within some error, we know that the weight of the parameters explain why that particular throughput was achieved. And then we know why things happened. Using the model achieves quite good results. We were able to achieve more than 90% accuracy in most of the cells. But like in the connection drop analysis, we found that there are a bunch of cells in the operator's network where the models, none of the models worked and predictions were really poor. The picture here shows the geographic location of the cells. I cannot show you where they are, but these are scaled to some random values. We see that the drops are concentrated and are occurring in a few cells. We investigated why this anomaly happened. One way to investigate that is you predict a throughput and you see what the actual throughput the UE obtained. You convert both of them to SINR values. You can figure out what SINR would result in the actual throughput and what SINR we use to predict, and then plot a difference between them, which is the loss of efficiency. We see that there is a loss of more than 10 dB for more than 20% of the bearers, which is significant. The operator was able to replicate this issue in their field tests and also in their labs. And their investigation resulted in the following finding, that the link adaptation algorithm uses a moving average. So what happens is that if the channel conditions change quite often, the moving average based link adaptation works pretty slow, and it results in throughput values which are not in correspondence to the SINR that the UE sees. To recap, we started with the question of whether it's possible to automate the diagnosis of RAN problems. Our experience strongly suggests that it is feasible. Our methods can be automated. The models can be automatically built, and these models can significantly reduce the time and cost effort for the operator. For example, in our drop scenario, if we just use the decision tree based model, most of the drops can be explained by these models, and the operator doesn't have to do any investigation at all. This converts to many millions of dollars. However, we learned that fully automating the solution for next generation cellular networks need much more work. We need to solve quite a bunch of challenges because the next generation networks need real-time diagnosis. And for doing real-time diagnosis, we need to build thousands of models, keep them updated, and make sure that they work all the time. We are actively pursuing this line of research, and we have made some progress towards it. What we found is that we don't have to build a model for every base station in the network. The models of these base stations have similarities. They are not geographical similarities. It doesn't mean that if a base station is close to another, the model applies to both those base stations. But there are similarities between base stations. The colors here show the number of models required, and the number of colors are small, which means that we could possibly group base stations and create and maintain these models in real time. So to summarize, I have explained our experience working with a tier 1 operator in the US over a period of 1 year. We showed that leveraging bearer level traces could be the key to automating RAN diagnosis. In doing so, we proposed a simple bearer level modeling technique, and we unearthed several insights using that. And finally, we have also learned that fully automating these diagnoses needs more effort. I'll stop here and take your questions.
Thank you, Speaker.